on congestion control enhancement, and we have some of the results that we want to share. So this is what we have for agenda. I'll kick it off with addressing some of the Ethernet for HPC market, and then challenges with PFC. And for the most part of the talk, we'll focus on the congestion control. And Moshe will transition at that point and go over some of the results that we have from OSU benchmarks, some of the application and GPC Net. And we'll share those results in our analysis. So that's we have for agenda. So real quick, it's been a number of years since RoCEv2 became standard. Ethernet now has been at the 100 gig and higher, and with the low latency implementation of Ethernet with high packet per second, it has reached a point where with 100 gig HPC market, Ethernet becomes, with RoCEv2, a solution to serve the workloads that HPC market traditionally use, either proprietary network or InfiniBand kind of networks. So this is from our standpoint, being in Ethernet market, very interesting transition point. And of course, with RoCEv2, what you get is the full offload as well as the kernel bypass. And when you support that with the SRRV, all the CPU efficiency that are built into the RDMA technology are available with RoCEv2 on the Ethernet side. And key here is you want to leverage the existing Ethernet infrastructure and the congestion control schemes which are deployed in Ethernet fabrics. And on the software side, there is well-established driver model, API layers have been stabilized verbs or higher level communication APIs, NPI, which is the focus of this conference here. So all those things, in short, they are coming together to make RoCEv2 based solution for HPC applications and workload. What we'll go over in this talk is showing some of those results. First, I think zooming into the MPI and communication topology. So as most of people on this call very familiar with MPI, this is the communication layer that's been used in HPC machine learning cluster environment where applications are seeing increasingly large and large scale. And scale goes here with the number of processes within a node, which basically reflects onto the what capacity you have in the node, number of CPU cores, and also the number of nodes that you scale within the cluster. And there are different algorithms which use different topology at the logical level, whether it's a ring level, binary cube tree, there are several of those. What happens is when you map those logical topologies to underlying network, and then when you use those with the collectives, it can create congestion in the network. And that's where how you manage that congestion basically helps you with how you scale the application and the performance scale. There is, that being said, there has been some ideas just around with RoCEv2 means you need PFC. So we want to first admit that PFC is not really required with RoCE. But what PFC helps initially is if you want lost as service, you start with PFC. It's a point-to-point protocol between two Ethernet endpoints. There are some challenges just deploying everything with PFC without congestion control. One is PFC by itself can result in congestion spreading. And that can basically result in offline blocking. Also, with slow receivers, you can run into this issue of you get into the PFC storm where what that means is you enter the PFC phase, get out of it, and then just to be entering it again. So this affects your network utilization. So that kind of PFC only solution can create, especially when you have slow receivers in a network or a receiver that is slowed down. And then there are also published papers where they have shown that sometimes PFC and with the deep kind of Tor leaf spine kind of architecture, and in those network, you may end up with some of the live locks within the fabric, and that can basically result in application stall or no progress. So these are some of the known challenges we have with PFC, but that's when you combine that with congestion control or use just the congestion control schemes that are at the endpoints and fabric, you can mitigate all of these issues, as well as you can look into having better scaling of application. So that's what we'll focus on for the rest of the talk. Let me hand it over to Moshe. He will first introduce the congestion control scheme, and then we'll go over the results. So Moshe.
Yep. Hi, everybody. Good afternoon. So the goal of the evaluation of our controller was twofold. One, to make sure that the controller is working properly at a very stressful environment in terms of the network, as well as the whole stack on the different machines. And secondly, to evaluate the differences or similarity in terms of the network configuration, where the network is lossless without any congestion control mechanism, or when the network is lossless with congestion control mechanism. And the third configuration is when the network is not lossless and only congestion control is enabled on the network. There is a lot of consideration to take into account when considering the PFC versus congestion control. One of the main differences is that PFC is a gross feedback from the network, where it does not distinguish between different flows and where these flows really need to arrive in the network. And it could be, the effect of that is that it could be blocking. By congestion control, work at the granularity of a flow, and it will only send a signal to flows that are actually causing the congestion, and only these flows will react and reduce their rate to reach a steady state that utilize the link, while not affecting any other flows that go to a path on the network that does not experience any congestion. So there were many tests that we used to evaluate from micro benchmarks, like Intel MPI benchmark or OSU benchmark, through things like HoRoVod machine learning testing of ResNet, GLUE communication library that developed for machine learning, through HPC applications such as molecular dynamic, weather forecasting, and high performance conjugate gradients. And on top of those, we also ran a benchmark that intend to test the effectivity of the network. It's called the GPC Net, that some of you may be familiar with it. And we will present some of the interesting results on that aspect that actually bring to the surface the effect of using PFC versus congestion control. So we'll start with a micro benchmark, which is OSU benchmark for collective communication. We can move to the next slide. That is, we tested the blocking and non-blocking collective benchmark test, and with a varying number of processes per node on a network with up to 32 nodes. And the intention is to see how the performance scale or changes as we increase the number of nodes that participate in the collective operation. We did the same for HPCG, which is a high performance conjugate gradient benchmark with 8, 16, and 32 processes per node, and similarly 8, 16, and 32 nodes in the system. And the third benchmark is for molecular dynamic, where the minimum unit is 32,000 atoms that are being simulated over 5 different types of benchmarks. But we use the scale test, where the more processes that we have in a network, the larger is the overall size of the simulation. And what is measured is the change in efficiency relative to only 32,000 atoms running on a single process. And of course, the higher the efficiency when you scale up the size of the simulation, the better. So we'll start with the OSU benchmark, and we'll move through the others. So, by the way, all the tests have run on 100 gigabit per second links in the 3 configuration. Again, just repeating the configuration: PFC, priority flow control without any congestion control, PFC with congestion control, and congestion control without PFC. This is really congestion control on a lossless network, on a lossy network, sorry. The third one. So for the OSU benchmark, of course, we don't have the time to go over all the evaluation we did. We bring here just sample of those, sample of the results. And this is a benchmark that is a standard benchmark that comes with the OSU. And what we show here is one of the more stressful type of collective, the all-to-all, and the way that the completion time is shown on the y-axis, while the size of the message is on the x-axis, and it's in kilobytes. So we see here from results from very small size messages all the way to 1 megabyte, and the top left chart is for all-to-all blocking benchmark with 4 processes per node over 32 nodes. And we see that the different color here, blue for PFC without congestion control, light blue for PFC with congestion control, and the orange for congestion control without priority flow control, are shown here. And on the bottom right, we see the similar results for the blocking benchmark for the same type of collective, which is all-to-all communication. So here we have 32 nodes that having passing traffic on the network. Of course, this kind of traffic, especially with the larger size messages, result in significant congestion in the network. And what we see here, the completion time, as it measured by the OSU benchmark across the different sizes and in under this heavy congestion. So this is basically a micro benchmark. We ran many such benchmarks, such as the all together and I all together, the blocking and unblocking version of those, or reduce. And we found that with all of these tests, we see that the scaling as well as the overall behavior of the network is very similar in all 3 modes. So the more interesting thing now to see is whether under a real application, not a micro benchmark where a single kind of operation is just repeated multiple times, a real application will present a real load on both the nodes, the system, and the network under a realistic kind of computation that is carried out in a distributed manner on the network. So the next one is the HPCG benchmark. We can go to the next slide, where the measure here is the G-flops per second as reported by the benchmark itself. The G-flops per second is on the y-axis. And on the x-axis, we see how the G-flops are scaling when we increase the number of nodes. And we can see here that we go from 8 on the left through 16 and 32. There are 3 marks that you can see on these charts. And we can see the similarity in the behavior and scaling over the different modes configuration. And it's basically a linear scaling of the GFLOPs. The more processes that we have for the computation, the performance of the system, of the whole system, is scaling up linearly. And we show that in the three charts with 8 processes per node, 16 processes per node, and 32 processes per node. So the maximum what we have is that we have 32 nodes by 32 processes per node, which result in 1,024 processes. We can see here that there are some small variation. Sometimes the results with PFC are a little bit better on the top right. Sometimes they are a little bit worse, but these are basically variation that are coming even from run to run in the same mode. So these are not accounting for any real difference in behavior in the different modes. We can go now to the molecular dynamic results. In the molecular dynamic results, we look at 4 different modes just for relative benefits of the RDMA operation versus traditional TCP. The charts that you see here for with the black color are for TCP. So there is no RDMA, no RoCE operation involved. We can see that the scaling or inefficiency as the number of processes are increased in the system is not very good with TCP. This is mainly attributed to the fact that the CPU is heavily involved in carrying out communication work, while with RDMA, the CPU is free to carry out mostly the computation and very little involvement in the network operation. The charts that we show here is only a subset of the overall evaluation that we did. We show the difference between the number of nodes from 2 all the way to 32 in each chart. But on the left side, we show the scaling, the inefficiency for 1 ppn, 1 process per node, on each of the node, versus on the right side with 8 processes per node. And we can see the scaling of the different modes. You can see the legend. We have the PFC without CC, which stands for PFC, priority flow control without congestion control at all, PFC with congestion control, and also congestion control without any priority flow control. In the LAMPS benchmark, there are different tests that are doing different kind of molecular dynamic simulation. These tests are laid out here. We see the first one is the LJ and the second one is EAM. And on the next slide, we have 3 more benchmarks. They have different type of communication versus computation patterns. But we can see a very good scaling in all of them in the 3 RDMA modes, and a clear benefit of the RDMA over TCP. The main point here is what's seen in the previous result, is that there is no performance or efficiency degradation, whether we're using PFC with or without congestion control. They all perform pretty much the same. We can show the results on the next slide now, Hemal, before we go to the test that actually show the difference between the different modes in a more clear way. So these are the other 3 type of molecular dynamic simulation that are done between 2 and 32 nodes with different number of processes per node. The last last benchmark is really the benchmark that try to see the network efficiency. We can go to the next chart, and it's called the GPC Net. In GPC Net, some of the processes are assigned test tasks, which the measurements is carried out over these test tasks. Things like all reduce, point-to-point latency, and neighbor exchange. And 80% of the processes in the network are carrying out what is called congestor tasks. These are basically heavy, either all-to-all or incast traffic that will create congestion in the network. And the way the test is performed is that the 20% of the test tasks are running by themselves on the network, and a measurement is taken as for the completion time of those. And then the test is repeated while the 80% of congestor tasks are running at the same time. And the aim is to try to find the effect of the congestor task on the performance of the test task, to see what kind of configuration or congestion algorithm and so on have more or less effect on the results. This is really measuring interference that may arise due to congestion between different threads or different flows that carry out communication and computation tasks at the same time, and they use a similar path on the network. So the way that the tool is reporting the result is by a factor of the results, for example, latency with congestor or without congestion. And the higher the factor, it means that the effect of congestor is higher, which is negative. You don't want the factor to be too high. We also take the very detailed dump from the results from the test, and we chart the distribution of completion time or latency for the different modes to see more clearly how the network behaving in terms of its effect on completion time. And this can be seen on the next chart. The chart on the left show a box plot for the baseline. The baseline is the test task running by themselves, and we can see that the distribution in terms of the 50% distribution, the P50, the P99, they all look very much the same for PFC, CCPFC, and congestion control only without PFC. They all very much the same, and this is very similar to what we've seen with all the other benchmarks that we showed earlier. However, when the same tasks are running with congestor, we see the distribution of, for example, a latency on the top right is staying very much unchanged for when congestion control is involved, which is the two charts to the right. But when congestion control is not enabled, we see that there is a huge spread of the latency results, which is a result of the fact that the PFC allow queues, a congested queue in the switches, to grow to a very large size, while the congestion control algorithm that is used on the controllers from Broadcom are minimizing the steady state queue growth to something that is around 100 kilobytes and no more, which allow traffic from flows that does not cause the congestion but go through the same path of congesting flow to fly through these switches that are congested much more quickly than when only PFC is enabled, and the queue size could be in order of megabytes. And this is the effect on latency with and without congestor. Again, there is another measure at the bottom for the one of them is the top is all reduced latency, and the bottom is point-to-point latency, and we can see the significant difference between allowing congestion control, enabling congestion control, and not enabling. The next chart shows the summary at the bottom from the benchmark tool itself. And could you move to the next chart, Hemal? Thanks. So we can see in the table, the left side is showing the left column is showing the type of test, and then we see the congestion impact, the average, and the P99, and we can see that there are three columns here. The red is the congestion control only, which means that the priority flow control is not enabled. The green one is congestion control with PFC, and the right one is PFC only. And we can see the huge difference in the factor of the congestor impact, which goes roughly between 1.8x for when congestion control enabled versus 120 or 30x when only PFC is enabled and congestion control is not in play. On the right side, and this is something that you would see that account for the interference that is caused by congesting flow, and it could come into play either when congestion control is not enabled or when the congestion control algorithm is allowing the switch queue to grow to a large size. And what's unique about the congestion control algorithm that is implemented here is that it uses an algorithm that is based on DC TCP, which maintain the queue level under congestion at a very low rate. What is especially interesting about adopting a DC TCP-like algorithm for RoCE is that unlike TCP, the stack, the latency through the stack on the host is very, very small. Relative to TCP, where software is involved and interrupt may be involved and so on. In RDMA, the stack involvement is practically zero. It's only the hardware controller that is implementing the transport protocol, and therefore the response is in microseconds. And because of that, there is the ability to maintain a very, very small queue level under congestion, even much better than what people are used to see with TCP with the TCP protocol stack. And that's the benefit of that is the interference between flows is minimized to a very, very, very small effect, as you can see here. To summarize, the next slide, please. RoCEv2 is designed to scale with no inherent limitation at the protocol level. We demonstrated here the performance up to advanced over TCP and with up to 32 nodes and many processes per node. With sophisticated congestion control, this can be done even without priority flow control, meaning on a lossy network. And the performance scale is excellent in all these modes. And just to keep in mind, with so many processes and so many nodes, the number of flows on each node is in the thousands, and the number of memory region used is in the tens of thousands. So the scale and the stretch over both the systems and the network is very high under this application that we presented here today.
Thank you. Thank you, Hemal and Moshe. Are there any questions? People can ask questions in the QA button or through the Slack. Do you have any on the Slack? I don't see anything. So Moshe, one quick question. So in your previous slide, so you showed like a 1.8x to 120x. The previous slide, if you see.
Yes, yeah, the one before that, Hemal. The one with the table. Yeah,
so PFC only is that like that is a degradation, if I understand. Is that correct?
Yeah, that's a degradation. The the all reduced latency and the point-to-point latency have the most impact when congestion control is not enabled and only PFC. And this is because the flows that create the congestion cause the queue buildup in the switch to go into megabytes, really. And the flows that try to do the short messaging between them, they have to wait behind all of this traffic before they can leave the switch.
Okay.
And the impact on the latency that these flows experience is huge when congestion control is not in play.
So you are advocating that the congestion control, that should be the primary one. That's what
it should be the primary one. Certainly. Yeah. People might be tempted that you could lower the threshold for PFC and then achieve a low Q level. But if you do that, you're basically blocking the whole network because of the way that PFC work, and it work at the granularity of not of a flow granularity. So if you try to lower the threshold of PFC, the network will come down to a halt very, very quickly. Yeah. And will stop traffic in paths that have no congestion at all.
Okay. So thank you. Are there any other questions? We have a Slack channel for every session, so please feel free to ask questions. And Hemal and Moshe, if you can just monitor the Slack channel for a little bit more time and then see if some questions come up.
Sure.
Thank you very much for the audience.
Thanks.
So thanks a lot again. So let's give thanks to Hemal and Moshe. So